Okay, so last class we talked about a special case of rectilinear motion, which is motion under gravity. And so moving on, we'll be talking about motion where you can best represent motion using a different coordinate system. It's in the path coordinate system. And so the learning outcomes for this class are we'll try to do position, velocity, and acceleration in normal and tangential coordinates. So this is 12.7 in the book. Okay, so when would you use this coordinate system? Well, in case where there's a path, and the best way to describe the path is through a variable, let's say s, which represents the path. So in rectangular coordinates, we're interested in motion in straight lines, right? In the x, y, z direction. In this case, we are given how the particle moves in the path coordinates. That is, s determines where the particle is on the path. If that's the case, then path coordinates are your choice for coordinate system. So to use this coordinate system, you need to know the instantaneous center of the arc or the particular path, and rho is the radius of that. So if you're on a circle, the center is the center of the circle. If you're on flat ground, then the center is at infinity, right? Because the radius of curvature is infinity. So what we do is, just like we have x, y, z, in this case, we have unit vectors in the tangential direction. This is always normal to the line which connects the center of that instantaneous circle. And un is the normal. This passes through the center O prime. Okay, so this rho is the radius of curvature. Okay, so an s is the path coordinate. Okay, so as I said, example, s is equal to r for circle, s will be infinity for plane. Okay, so circle, that's r. For plane, it's going to be infinity because the radius is at infinity. Okay, so once we have that, then just like we express the position, which is as a function of s, we can find the velocity and the acceleration. So velocity is v, and that is simply the derivative of s okay. Ut is the, as I said, it's the tangential coordinate. Okay, if you like, you can call it v. And then there is acceleration, which is the derivative of v. So a is dv dt. So all you got to do is take this expression for the velocity and differentiate it once. And I'm not going to do that, but what comes out of it is s double dot ut plus s dot square divided by rho, or the radius of curvature, times un. Okay, and the reason why, well, so if you take the derivative of this, you have the derivative of the first term s, which is s double dot, right? And the second is going to be derivative of ut. That is not zero, because remember what happens is ut is this particular tangent, right? It changes with time. It keeps changing. So ut is not constant. That's why when you try to take the derivative, you'll get s dot ut plus s times ut dot. And turns out that ut dot is s dot square divided by rho times un. Okay, the derivation is in the book. Yeah?
Clarification, the velocity, is that a s dot ut or vt?
It's ut. So ut un.
Professor, we set that second equation up just as a second order differential. Is that with respect to time or position?
Which one? For the acceleration? The second expression, this one? It is, this is again with respect to time. This s ds dt is, s dot is ds dt. So when I say s dot, when I have a dot in this class, it would mean time. If it's with respect to x, then I will specifically say ds dx. So anything in this class, this is going to be, the dot is time, with respect to time. Okay, so what I'll do is I'll write this as, in terms of v, v dot plus v squared divided by rho un, and so this is my final expression for acceleration. Okay, so this is v dot is the rate of change of velocity, the first term. The second one is v squared divided by rho, and that is something which we normally called, have you heard of centripetal acceleration? That's the centripetal acceleration. This is the acceleration which you feel when you're going in circle. If you start turning around yourself like that, you'll feel, well, if you turn about, on a carousel, when you feel thrown out of the carousel, that's because of this particular expression. It's v squared divided by rho. So we'll come to the force and acceleration again when we do chapter 13. Okay, now one question here is, how do you find rho, right? For a circle, rho is simply, my bad, this should be rho. Just correct this should be rho. Okay, for a circle, we know rho is r, right? For a plane, we know it's infinity, but what about like a parabola or a square, where square is going to be infinity? So how do you find rho? Well, it turns out that there is a formula from calculus, and I would not expect you to derive this. If y is f of x, okay, so this could be, for example, y equals x square, which is parabola, right? Then you want to find rho over here, rho over there, and so on, right? So how do you find rho? Well, rho is given by this expression. Rho is 1 plus, move things around a little bit. Okay, so rho is given by 1 plus dy dx the whole square. This whole thing, you need to take the cube and then take the square root, divided by d square y dx square. Okay. So this is a formula for rho when the geometry of the curve is sort of weird. It's not standard. It's not a circle, nor is it a plane. Okay, so right now here this derivative is with respect to x and not with respect to time. Okay. Okay, so I also forgot to put an absolute sign. The absolute sign means that if the value here comes out to be -3, it is to be taken as +3. This is the absolute value. So minus 5 is 5, plus 5 is just 5. Okay, any questions on this? Zoom? Okay, let's do a basic problem and then go to harder ones. Okay, so this is the question. Okay, so an automobile is traveling on a curve having a radius of 800 feet. If the acceleration of the automobile is 5 feet per second square, determine the constant speed at which the automobile is traveling. Okay, so first of all, why would you do this in path coordinates and why not rectilinear coordinates? Well, you're told the radius is 800 feet. The moment it says radius, then what should ring in your head is what you should think is, well, if there's a radius, it should be in path coordinates. Okay, so try doing this. Let me put down things we know about. So we know rho is 800 feet. You're given that the acceleration is 5 feet per second square. Now, mind you, you're given the absolute value. Okay, if you were told the actual value in terms of a vectorial quantity, then you would be given the tangential component is so and so and the radial component is so and so. In this case, you're not given that. Okay, so then you got to find what? Find V. Okay, can you find V given these three things using the formula which I just wrote down? Can you got the answer? Okay, let me give you a hint. So what's the magnitude of the acceleration? If you know that the acceleration in path coordinates is this, it's v dot square, right, plus v squared divided by rho, the whole square, and then the square root. Right? Now, can you try to get can you try to find v? Anybody got the answer? No? How will you proceed from here? So you kind of know what V is, right? V is, well, sorry, you don't know what V is. You got to find that. You know what rho is. It's 800 feet. Okay. You know what the acceleration is. It's 5. So V square. So V raised to 4 divided by rho square. So it's 800 square. And so you don't know what V dot is. What's V dot? What's V dot? What? Acceleration is 5, but I already wrote that down. What is V dot? It's 0. Why is it 0? It's because if you read this question carefully, it says find the constant speed. Okay, so the speed V is constant. It doesn't change with time. So V dot is 0. So you got to solve for V, and what I get is 8.66. Any questions? Yeah.
In the book, it says like the magnitude of the acceleration is the square root of at squared plus an squared.
At squared plus, yeah, so at, so the book says a is at ut plus an un, and at is the tangential component, which is v dot, and the normal component is v squared divided by rho. So it's the same thing. They just write it in a different way. The reason why at is called the tangential is because it's associated with with t, and an is the normal component because associated with un. So ut, so at is this, and un is this, so this is an. Okay, this is just a notation. Any other questions? What's that? How will you compute that? Well, so I can't hear you. Oh, well, I'll do problems where v dot would change. So one case you would be told what s is, and then you can take the second derivative. S double dot is v dot, right? And you can find s. But otherwise, you'll be given what s dot is. Sorry, v dot is, or you'll be asked to find v dot. Yeah. 63.2. Oh, sorry, my bad. Yep, it's 63. I was looking at the wrong answer in my notes. Let's solve this problem. So the automobile shown here has a speed of 80 feet per second at point A, as shown there. The acceleration is of magnitude 10 feet per second square, acting in the direction shown. Okay, so this is the acceleration. Okay, and you also given the direction. You got to find the radius of curvature of the path at point A. So there's obviously a rho here, and then you need to find the tangential component. So the tangential component is AT is this way. So this AT, this is going to be AN. So let's see, what we know is V, that's 80 feet per second. And then we know what the magnitude is. This is 10 feet per second square. And we are asked to find rho. And then we also asked to find AT. So first thing I can think of is, we know what A is, right? A is AT UT plus AN UN, and that is V dot UT plus V square divided by rho UN. So what we are given is the magnitude, which is V dot square plus V raised to 4 rho square. The whole thing is under the square root sign. So, okay, AT is simply V dot, right? So if we can find V dot, we found what AT is. We also asked to find what rho is. And we are given what V is. We know what V is. This is known. Okay, so, and A is known, of course. So we have one equation, right? And there are two unknowns. You cannot solve, you cannot get a unique solution if you have one equation and two unknowns. So we need one more piece of information to solve this problem. So what is that piece of information? Are we given something else we can use? Theta. So we are also given theta. Okay, saying that the acceleration vector makes an angle of 30 degrees with the tangential direction. So there are a number of ways you can use this. You can, well, if you know theta, then you can use, in this case, I would use the tangent of theta. Sorry, the cosine of theta. So let's see. So I'm going to redraw this, just this part. AT, and 30 degrees. Okay, so I know that A is what, 10. I know the angle is 30. I don't know what AT is, and just by looking at this figure, can you find what AT is? So AT is A cosine. So this is A cosine of 30 degrees, right? It's cosine of 30 because you can draw a right angle triangle like this, and then that's the cosine of, cosine is basically the adjacent side divided by the hypotenuse. So AT is 10 times cosine 30. Cosine 30 is sine 60, which is 0.866, so it's 8.66 feet per second. Okay. Okay, so AT is also V dot. AT is V dot is 8.66 feet per second. So we've solved for one of the unknowns. We still have to solve for the radius. So now what we have is, I know what the acceleration is. I know what V dot is. It's 8.66. I know what the velocity is. That's 80 feet per second. So that's raised time raised to 4, and then the rho is unknown. So now I have one equation and one unknown, the rho. Solving for rho gives me so I get 1280 feet. Okay, so you'll see that in all these questions, it's basically very basic linear algebra. You write n equations, and you better have for n unknowns and solve for those unknowns. We would not see a design problem. A design problem is when you have less number of equations and you have one equation and more number of variables. So for example, if you have one equation and 5 constants there, 5 variables you need to determine, then those kinds of problems are design problems, because you can choose one of them and vary the others. And so these usually occur in your design classes. They will not occur in sophomore level classes. We'll give you x equations and there'll be x unknowns. And if you cannot get x equations, x unknowns, you've got to look carefully to find those equations. Okay, is there any question on this? Okay, so here's a problem where v dot is not 0. Okay, I'll do another problem where v dot is not equal to 0. Okay, so a box is sliding along a curved path defined by the parabola y equals 0.4x square. When it is at A, this point, the coordinates are x equals 2 meters, as shown here, and y is 1.6, so the y is 1.6. Given the speed is 8 meters per second. Okay, so v is 8 meters per second. What else? They're given the increase in speed. V dot is 4 meters per second square. You're going to find the magnitude of the acceleration of the box at this instant. So just the magnitude. So again, you'll use path coordinates for this problem because you are given velocity and rate of change of velocity, and this is defined for a parabola, and it's no clear way of, well, you could actually do this with rectangular too, because you're given the curve y equals 0.4x squared. Now you can do this problem with rectangular or with usual path coordinates. Let's try to do it with path coordinates. And I'll try to do it with rectangular coordinates. So A equals v dot square plus v dot. So I'm skipping a step. I'm not writing the expression for the acceleration in path coordinates. I'm directly writing the magnitude. Okay. So v dot is known, v is also known, this is known, this is known. We got to find this, and rho is an unknown. However, we know how to find rho, right? Rho is 1 plus dy dx square Okay, so we need to find dy dx and d square y by dx square. We know that y is 0.4x square, so y is 0.4x square. So dy dx is 2 times 0.4 times x, and d square y by dx square is 2 into 0.4. Okay. And in order to find rho, we need a value for rho. It's the radius of curvature. So we need to find the rho when y is what, 1.6 and x is 2 meters. So I can put x equals 2 to get so this is 2 times 1.6. X equals 2 is just 0.8, doesn't depend on x. So when you put this thing in the expression, you get rho equals 8.39 meters. So once you get rho, you can solve for A, that's 8.61. So we okay, is that clear?